Okay, we're having a part B of this lecture on model-based system engineering. We covered all the content, but at the latter part, we're also going to be talking about examples, and that's what we're going to be addressing here. So make sure you watch the first part, and you'll get a chance to see that. So here are a variety of examples of model-based system engineering diagrams. We'll see some of them that are in the SysML format and a few other things. And so this first one will be showing some information about the Apollo spacecraft. So this section provides examples of how a system may be represented in SysML. And so this one is a SysML block diagram showing the structure of the Apollo spacecraft. It uses compartment notations to display interfaces such as telemetry. Other features such as part properties, functions, or constraints could also be displayed. So that's something that you can keep in mind. So this representation shows a structural information from the Apollo model in a relationship map. This is a tool-specific representation and not specified by the SysML standard. So sometimes these additional types of ways of looking at things can be of use. This figure shows the same information in a matrix. This is an example of how model information may be extracted and displayed in a variety of formats to meet the user needs and expectations. And so here you can have things in a tabular type of format. Here is an example for vehicle part properties. Tabular representation of model informations are particularly useful. They may be exported to Microsoft Excel or other spreadsheets for further analysis. So the figure here shows a summary of the part properties that make up the launch vehicle, and updates to the model would be immediately reflected when the table is reopened / refreshed. Modifications made to the information in the table, such as changing the multiplicity or type of part property immediately cascade through the model. So here is an example of another SysML diagram called the internal block diagram, or IBD. The interfaces between model elements may be represented via the SysML internal block diagram. So this figure shows the connection between elements of a notional satellite command and data handling subsystem. Port types such as CAN bus are defined once and reused throughout the model to ensure consistency. Here we have an illustration of a state machine. So the SysML state machine diagram for a satellite's flight control subsystem is seen. And then the next figure will have something more complicated. It's the state machine for the redundant flight computers, for each of the redundant flight computers. The state machine diagrams express the various states in which a subsystem and computer may operate and the behaviors and transitions associated with each state. Each transition is rigorously described. That is, what triggers it, what behaviors occur during the transition, and what conditions must be met to initiate the transition. All the information in this diagram may be summarized in tabular form. This is useful for many analyses. For example, safety analysis may require detailed review of allocable transitions into one of the potential hazard states. Tabular information, which can be stored and filtered, eliminates the need to manually trace lines on the diagram. Here is the other one. This is a little bit more complicated. So we have this simple state machine diagram, and now we have this more complicated one here. Okay, moving on, we have a parametric diagram. This relatively simple parametric diagram represented in this figure shows how values in the model may be related via reusable constraint block elements. These diagrams permit a graphical representation of the related variables or source and the equations that relate them. The next figure we'll show in a second, it shows a more complex diagram that relates properties describing a vehicle driveline. And so note there are references in the textbook, and so I would have you go to them for more of those details. And so I know this is not going to be readable, but it just gives you an idea of the extent of what you can be doing with a couple sample SysML diagram types. And so I blew this up. And so this is the top part of this diagram. And so this is the bottom part of that diagram. You can pause the video and feel free to review that as long as you would like. Okay, well, let me do a summary review of the material that we've talked about. We talked about in MBSE introduction, the continuing growth in system complexity is driving the practice of systems engineering from a document-intensive approach to a model-based discipline. This enables the exchange of engineering information via descriptive system model and related information, either directly or using derived work products. Because information exists in a single authoritative data store, stakeholders and the engineering team access an integrated, synchronized description of system intent instead of disconnected documents that grow out of alignment over time. System engineers need to become knowledgeable of MBSE to appropriately include modeling tools in system development. In terms of model-based system engineering languages, various system modeling languages have been created to facilitate the development of models and related artifacts. SysML is the current modeling language used to develop products for system development in a model-based approach. SysML borrows heavily from UML and adds unique diagrams to address system unique needs, such as the requirements document, block definition diagram, and parametric diagram. We showed examples of all three of those. In terms of model-based system engineering tools, the system engineer must have some proficiency in the tool used to develop the MBSE products. There are different advantages and disadvantages to learning and using the tools for MBSE purposes. Advantages include ease of product exchange, configuration control, and interoperability of design information between the system engineering team members. Disadvantages may include the initial cost to gain tool proficiency, time and cost to maintain tool proficiency, and need to have stakeholders and partners accept the MBSE approach. For MBSE use in the system engineering lifecycle, system models may be used throughout the life cycle of a system. In the early phase, it can help with capabilities, objectives, and the overall system context, and system context can be captured. For the architectural development phase, it can help automated trade studies, requirements compliance, and derived work products. Those all can be developed. For the testing phase, it can help with architectures, test procedures, and test infrastructures. Those all can be modeled. For the operations and maintenance phase, requirements, test results, interfaces, and properties can all be represented. For the retirement and disposal phase, identification of components that require secure disposal, failure, and warranty analysis, those can all be done with MBSE. All right, well, thank you very much.